A stone fortress crumbled not from a mighty army, but from a simple crack in its design. We are about to uncover the 20 hidden engineering flaws that caused the collapse of mighty medieval fortresses. By the end, you will hold the blueprints to history's greatest structural failures. We will reveal why the strongest walls fell and how a fortress's greatest strength could secretly be its fatal weakness. What is the one mistake you would never want to make when building something meant to last forever? The ground beneath a fortress holds secrets no eye can see. Before a single stone was laid, a critical decision was made, one that would determine the fate of the entire structure for centuries to come. That decision was where to build. Medieval engineers, for all their skill, were often blind to the hidden composition of the earth. They would choose a site that looked perfectly solid, a high hill with commanding views, never knowing it was composed of deep layers of clay or loose, shifting sand. Without modern tools for soil analysis, they were building on a mystery. The foundation, the very platform of their strength, was a gamble, and time always collects on those bets. You can see this slow-motion disaster in the story of the Château de Coucy. Its mighty keep, designed to be an unbreachable stronghold, began a silent, sinking descent into the earth almost from the day it was completed. This was not a dramatic collapse but a creeping failure. Year by year, decade by decade, the ground beneath it compacted and settled unevenly. The immense weight of the stone caused the unstable substrate to shift, leading to cracks spiderwebbing through the lower walls and a noticeable, alarming lean in the towers. But the problem went deeper than just soil. A poor understanding of hydrogeology, the movement of water underground, created an invisible enemy. Water would seep through the earth, slowly washing away the fine particles that gave the ground its stability, like a constant, gentle erosion from below. This created hidden voids and cavities that further undermined the foundation's support. The fortress was not just sinking, it was being hollowed out from its very base. This initial, invisible misstep in site selection set an inescapable countdown to failure. It proves a timeless principle that a fortress, no matter how mighty, is only as strong as the ground it stands on. A weakness hidden below will always find a way to show itself above. The very glue that held these stone giants together could secretly betray them. Medieval mortar was not the uniform, engineered substance we use today. It was a recipe passed down through generations, and its quality varied wildly from one batch to the next. The primary ingredient was lime, created by burning limestone in a kiln. But if the limestone was not heated to a high enough temperature, a process called underburning, the resulting lime would be weak and ineffective. When mixed with sand and water, this poor quality lime failed to create a strong chemical bond. Think of it like trying to build a sandcastle with dry, dusty sand instead of wet, cohesive sand. The mixture would lack the essential stickiness to hold the heavy stones together for centuries. Sometimes masons would stretch their expensive lime by adding too much sand. While this saved money in the short term, it created a brittle, crumbly mortar that offered little more than a placeholder between blocks. Under the immense, constant pressure of the wall above, or the sudden, violent impact of a siege engine, this subpar mortar would simply turn to powder. The stones, once locked in place, would begin to shift and grind against each other. Historical surveys of castle ruins often point to this exact issue. Sections of wall that collapsed during a bombardment or an earthquake frequently show mortar that is friable and disintegrated, while the stone itself remains intact. The wall did not fail because the stones broke, but because the bond between them gave way. This underscores a fundamental truth that the strength of a structure depends on the quality of its most humble components. A single weak link, even one as seemingly insignificant as the mortar, can compromise the integrity of the entire fortress, and the danger did not stop at the materials themselves. The very shape chosen for these mighty walls introduced a shocking vulnerability, a design flaw that would turn their greatest asset into a critical weakness. The geometry of a fortress's towers was a matter of life and death, and the common square design held a fatal secret. While these angular towers were simpler for stonemasons to build, their sharp corners created dangerous blind spots known as dead zones. A defender standing on the wall walk between two square towers could not see the base of the wall directly below him. An attacker could approach this vulnerable spot completely unseen, shielded by the very shape of the defense. This allowed sappers to work undisturbed, starting the slow, deliberate process of digging a tunnel to undermine the wall, or for soldiers to simply set up ladders without facing a barrage of arrows or rocks from above. The corners themselves were also a structural liability. Under the immense impact of a trebuchet's projectile, the force did not flow smoothly around the tower. Instead, it concentrated at the sharp 90-degree angles. These corners acted as focal points for stress, much like how a small crack in a car windshield can spread across the entire pane from a single point of pressure. This made the corners the most likely place for major cracks to form, potentially leading to a catastrophic section of the wall shearing away. The famous siege of Rochester Castle in 1215 provides a stark example. After undermining one entire corner of the Great Square Keep, the besiegers used the fat from 40 pigs to fuel a fire that collapsed the timber props in their tunnel. The entire corner of the massive stone structure crumbled into the moat, a direct result of exploiting the inherent weakness of the square design. This dramatic failure was a harsh lesson that resonated across Europe. Engineers began to phase out square towers in favor of rounded ones. A round tower eliminated blind spots, giving defenders a clear line of sight along every inch of the wall. More importantly, its curved surface distributed the force of an impact evenly around its circumference, deflecting projectiles and resisting concentrated stress. This evolution from square to round was a clear case of form finally following function, a direct response to a devastating engineering flaw. Yet, even as walls grew stronger and designs smarter, builders were about to discover that reaching for the sky came with its own profound set of dangers. Reaching for the heavens seemed like the ultimate declaration of power, but it came with a hidden price. In the race to build the most imposing fortress, engineers often pushed vertical limits without fully understanding the consequences of height. A taller keep was a potent symbol of dominance, visible for miles across the countryside. Yet, this grandeur created a top-heavy design that placed enormous stress on the foundations we now know were often inadequate. The immense weight of stone stacked so high created a precarious balance, like a child stacking blocks too tall and too thin. This was especially dangerous during a storm, as the large surface area of these towers acted like a sail, catching the wind and generating powerful lateral forces that could shake the entire structure. In earthquake-prone regions, the effect was even more devastating. The tall, rigid towers would amplify the ground's shaking, swaying violently at the top while the base struggled to keep up, leading to catastrophic failure. A stark reminder of this flaw occurred with the bell tower in Pavia during the 9th century. Built to an impressive height, it stood as a landmark for the community until one day, without the drama of a siege, it simply collapsed. The cause was not an enemy army, but its own staggering weight and high center of gravity. The force of gravity itself, acting on this massive, elevated block of stone, created what engineers call an overturning moment. Essentially, the tower became a giant lever trying to pivot at its base, and the foundation could not provide enough resistance to keep it upright. This case teaches a crucial lesson that echoes through all of engineering, that the desire for grandeur must always be balanced with gravitational practicality. A fortress needed to be intimidating, but first it needed to stand, and as builders grappled with the forces of wind and weight, they faced another elemental challenge, one that could both defend a fortress and secretly plot its downfall from within. Water is a patient and relentless enemy. While moats were designed to keep attackers at bay, the water that collected inside the fortress walls was a far more insidious threat. Many of these stone giants were built with a critical oversight, inadequate drainage systems that allowed rain and runoff to accumulate in the very places it could do the most harm. Internal courtyards, designed as the bustling heart of the castle, would often turn into shallow, stagnant ponds after a heavy storm. This standing water did not just create a muddy inconvenience, it seeped down slowly and persistently into the ground around the foundation. Over time, this constant saturation turned stable soil into a soft, unstable slurry, undermining the support for the massive walls above. You can witness the long-term effects of this at Dunstanburgh Castle in England. Its dramatic ruins on the coast were not just shaped by time and battle, but by chronic waterlogging that eroded its base and destabilized the very earth it stood upon. But the damage did not stop at the foundation. The masonry itself was under attack. In colder climates, this trapped water became a powerful destructive force through a process called the freeze-thaw cycle. Water would seep into the tiny pores and cracks of the stonework. When nighttime temperatures dropped, that water would freeze. As water turns to ice, it expands with tremendous force, acting like a tiny wedge that pried the stone apart from within. Then, when the sun rose and the ice melted, the water would flow deeper into the newly widened crack, only to freeze and expand again the following night. This relentless cycle, repeated over hundreds of winters, could slowly pulverize solid rock into gravel. An effective defense required more than just a moat. It needed an intricate network of channels, gutters, and underground conduits designed to whisk water away from every critical structural element. The absence of this simple, vital system proved that a fortress could be silently dismantled not by a siege, but by the rain and frost. After all, the most obvious point of entry was often the most heavily defended, yet it still held a fatal weakness. The gatehouse, the grand entrance designed to intimidate, was often a collection of hidden flaws just waiting to be exploited. The grand gatehouse stood as the ultimate test of a fortress's strength, a monumental entrance designed to awe and intimidate. Yet this very complexity often concealed its own undoing. While multiple portcullises, heavy wooden doors, and murder holes created a deadly funnel for any attacker, they also introduced a series of structural joints and stress points. Each archway, each gate, and each mechanism represented a potential failure zone where the continuous strength of the wall was interrupted. If the foundation beneath this intricate structure settled unevenly, a common issue we have already explored, the entire gatehouse could twist and warp. This misalignment would prevent portcullises from dropping smoothly, jam doors in their frames, and most critically, create cracks in the vital stone arches that bore the immense weight of the gate tower above. These arches were the skeleton of the defense, and a flaw in their construction or support could bring the entire complex system crashing down. History offers a sobering lesson in the siege of Constantinople in 1453. The city's legendary Theodosian walls had repelled invaders for 1,000 years, but their gates became the focal point of the Ottoman assault. The relentless bombardment from massive cannons concentrated on these critical junctures, exploiting the inherent vulnerabilities where one defensive element met another. The gates, for all their layered protection, ultimately became the breach point that decided the fate of an empire. In response, engineers gradually evolved their designs. They learned to simplify the load-bearing structures within the gatehouse, creating more robust archways that distributed weight more effectively. They also designed barbicans, fortified outworks that forced attackers into narrow, exposed channels covered by overlapping fields of fire from the walls. This approach protected the main gate from a direct, concentrated assault. The lesson of the gatehouse is clear that overcomplication can breed fragility. A design with too many moving parts, too many intersections, creates more opportunities for a single point of failure. But the problems were not always in the design. Sometimes they were baked into the very materials meant to provide unshakable strength. The very stones chosen to build these fortresses could wage a silent war against each other. Medieval builders, working with the materials most readily available, often combined different types of stone in a single wall. They might use a hard, dense granite for the foundation and a softer, more workable sandstone for the upper sections. This seemed like a practical solution, but it ignored a fundamental physical principle. Every type of rock reacts differently to changes in temperature and moisture. On a hot summer day, sandstone expands significantly more than granite. Then at night, as the temperature drops, it contracts more. This differential movement, happening day after day, year after year, created immense internal stresses within the masonry. The stones were literally pushing and pulling against each other, fighting for space. This relentless conflict would eventually fracture the weaker stone or, more critically, the mortar holding them together. The result was not a single dramatic crack, but a slow, grinding disintegration from within. You can see this legacy of material conflict at the magnificent Crack des Chevaliers. Surveys of its walls reveal cracks and spalling that follow the seams where different stone types meet. The incompatibility of the materials exacerbated damage from earthquakes and sieges, creating fault lines that nature and enemies could exploit. The lesson is one of harmony. A fortress built from a chaotic mix of materials, no matter how strong each one is individually, creates its own points of failure. The structure is only as unified as the materials from which it is made. This internal discord was a flaw baked into the very fabric of the walls. But what if the entire defensive scheme, the grand strategy of the fortress itself, was flawed from the start? A fortress's defensive wall was only as strong as its connection to the tower beside it. These long stretches of masonry, known as curtain walls, were designed as seamless, continuous barriers. Yet the joints where these walls met the fortress's larger towers were often points of catastrophic failure. Builders frequently constructed the tower and its adjacent wall as separate entities, sometimes even at different times. Each structure had its own foundation, and if that foundation settled at a slightly different rate, a hidden fissure would begin to form. What appeared from a distance to be a single, unbroken stone face was in fact a hairline crack running from the base of the wall right up to the battlements. This tiny separation was an open invitation to disaster. During a siege, the relentless pounding of a battering ram or a trebuchet concentrated on this joint could cause the two sections to shift independently. The crack would widen into a gap, and the wall would literally peel away from the tower, creating a breach exactly where the defense should have been strongest. The history of the Castle of Geysers in the 12th century provides a sobering case study. Its formidable defenses were repeatedly compromised not by the collapse of a tower or a wall, but by the failure of the connections between them. Attackers learned to target these junctions, and the stonework, unable to act as a unified whole, gave way at its seams. the engineering lesson was brutally clear. A chain is only as strong as its weakest link, and for a curtain wall, that link was always the joint. The solution, developed through painful experience, was to build curtain walls and towers with interlocking stonework, bonded together from the very first course and resting upon a single, continuous foundation that would settle as one solid mass. This ensured the entire structure would move and bear stress as a single entity. Yet, even as engineers solved one problem, they often created another in the pursuit of something beyond pure defense, the dangerous allure of architectural beauty. Even beauty could be a fatal flaw. In the relentless pursuit of both security and status, castle lords sometimes commissioned elaborate decorative features that secretly sabotaged their walls from within. Oversized crenellations, the tooth-like parapets atop a wall, were not just for show, they were meant to provide cover for defenders. But when these stone blocks were made too large and ornate, their excessive weight placed a dangerous, concentrated load on the edge of the wall walk. This created a constant downward pressure that the wall below was never designed to handle, leading to cracks that snaked downward from these points of stress. Similarly, the elaborate corbels that supported machicolations, those projecting galleries from which defenders could drop objects on attackers, were another hidden risk. While a simple, robust stone bracket would have been strong enough, architects often carved these supports into intricate figures of animals or saints. The detailed carving process removed crucial mass from the stone, creating microscopic fracture lines and weak points that could fail under the immense weight they were supposed to bear. The mighty Malbork Castle, the largest brick castle in the world, offers a stark example. Investigations into its structural history have revealed that the collapse of certain sections was directly linked to ornate, load-bearing elements. The decorative stonework, while breathtaking, had simply not been engineered to carry the tons of masonry above it for centuries. The stone eventually gave way under a burden it was never meant to carry in its embellished form. These aesthetic choices also had a direct military cost. Intricate carvings and sculptural elements on the outer walls provided perfect handholds and footholds for agile climbers, turning a smooth, defensible surface into a makeshift ladder for a stealthy assault. This critical error teaches us that in defensive architecture, every single element must serve a purpose. When form is allowed to overshadow function, the structure's very survival is put at risk. And just as the outside could be dangerously decorated, the internal layout of a fortress could create a death trap for its own defenders. A fortress could be defeated from the inside by its own blueprint. The most brilliant external defenses were rendered useless by an inefficient internal layout, where narrow stairways, tight corridors, and cramped courtyards created a maze of fatal choke points. During a peaceful day, these passages were merely inconvenient, but in the chaos of an assault, they became a death sentence for the defenders. Imagine a small breach in the outer wall. The alarm sounds and soldiers rush from the keep to reinforce the threatened section. Instead of a clear, wide path, they funnel into a single, twisting staircase or a narrow gatehouse passage. The result is a paralyzed mob, a bottleneck of armored men unable to move forward or retreat, while enemy soldiers pour through the breach unimpeded. The design of Chateau Gaillard, built by Richard the Lionheart, serves as a legendary cautionary tale. Its innovative concentric walls were ahead of their time, but its internal courtyards were segmented and difficult to navigate. During the siege of 1204, French forces discovered a secret latrine chute that allowed them to infiltrate the chapel courtyard. Once inside this confined space, they secured a foothold. The castle's own layout prevented the English defenders from mounting an effective, coordinated counterattack to this unexpected internal breach. The invaders then systematically fought their way from one cramped courtyard to the next, exploiting the very defenses meant to compartmentalize an attack. The fortress fell not because its walls were weak, but because its defenders could not move freely within them. An effective design required clear lines of movement, wide enough for armed men to run side by side, with multiple routes to any critical defensive point. This allowed for a dynamic response, turning the entire fortress into a reactive organism rather than a collection of isolated, suffocating boxes. The failure to plan for internal mobility proved that a breach in the wall was only the beginning of the end. The real collapse happened in the crowded, chaotic passages where defense turned to disarray. But a fortress was more than just its walls and internal passages. Its survival often hinged on the vulnerable structures that lay just outside its main defenses. A fortress's outer defenses could become its own worst enemy. Barbicans and outer walls were designed as a first line of defense, a brutal filter to break the momentum of an assault before it ever reached the main gates. Yet if these outworks were not seamlessly integrated with the primary fortress, they transformed from a protective shield into a deadly gift for the attacker. A poorly connected barbican, accessible only by a narrow, exposed bridge or a single gate, could be swiftly isolated by a determined enemy. Once captured, it was no longer a defense, it was a fortified camp for the besiegers, providing them with ready-made stone cover and a perfect platform to launch their next assault directly at the heart of the castle. The siege of Kenilworth Castle in 1266 demonstrates this flaw with devastating clarity. The attackers focused their entire effort on overwhelming the extensive but disconnected outer works. Once these fell, the defenders were forced to watch from the high keep as their enemy calmly organized within the very defenses built to stop them. The outer walls became a siege workshop and a barracks, and the inner walls were exposed to a relentless, close-range bombardment they were never designed to withstand. This failure highlights a vital principle of layered defense, that every layer must be able to support the others. A barbican needed covering fire from the main walls, and the main walls needed the barbican to disrupt and delay. Without this mutual support, the layers did not strengthen the whole. They simply created a sequence of smaller, easier targets for an enemy to conquer one by one. This concept of interconnected resilience echoes far beyond medieval walls into the design of modern cybersecurity and military strategy, where a single weak link can compromise an entire network. Yet the ground could betray a fortress in ways far more dramatic than just a slow, sinking foundation. The earth itself could deliver a blow more devastating than any siege engine. While the slow creep of a poor foundation was one threat, a sudden, violent tremor was another matter entirely. Builders often chose locations for their strategic views or defensive inaccessibility, completely ignoring the seismic reality of the land. They raised rigid, inflexible stone fortresses in regions where the ground periodically shook, a catastrophic mismatch of design and environment. A fortress designed to resist a steady, downward force from gravity and a horizontal push from a battering ram was utterly unprepared for the chaotic, multidirectional jolt of an earthquake. The walls, lacking any capacity to flex or absorb the energy, would simply crack apart at their weakest points, often the mortar joints or the connections between towers and curtain walls. The legendary Alamotte Castle, the stronghold of the assassins, stands as a haunting testament to this flaw. Perched high in the Alborz Mountains, a seismically active zone, its ruins today show fractures and collapses that align far more with tectonic violence than with any military conquest. The ground it was built upon ultimately proved to be a more formidable enemy than any army that laid siege to it. This fundamental oversight underscores a principle that modern engineers take as gospel: you must design for the specific hazards of your location. A structure in California is built to sway with an earthquake, just as one in Florida is elevated against hurricane surges. Medieval builders without this knowledge were essentially gambling with the planet's volatility. And just as the Earth could shake a fortress apart from below, the structure's own protective roof could conspire to crush it from above. A seemingly secure roof was often a hidden time bomb of weight and decay. The vast, sprawling roofs of great halls and towers were engineering marvels in their own right, but their immense weight was a constant, pressing danger. Constructed from heavy timber frames covered in stone tiles or lead sheeting, this roofing system could weigh hundreds of tons. All of that colossal load was transferred down through wooden beams onto the tops of the stone walls. Over centuries, this relentless pressure could cause the walls to bow outward, a phenomenon known as spreading. The roof was essentially trying to push the walls apart, and without adequate bracing, it could succeed. The true danger, however, often lay hidden in the dark, enclosed space of the attic. The timber frames that held up the roof were vulnerable to two silent killers, rot and wood-boring insects. Poor ventilation trapped moisture against the ancient beams, creating a paradise for fungi that slowly ate away at the wood's structural integrity. A beam that looked solid from the outside could be hollowed out and crumble to dust at the slightest provocation. When a key supporting timber failed, it did not do so quietly. The sudden redistribution of weight could overstress the remaining beams, triggering a domino effect that ended with the entire roof structure collapsing inward, often bringing large sections of the upper walls down with it in a cascade of stone and splintered wood. The integrity of the entire fortress, from its highest peak to its lowest foundation, relied on this delicate balance, proving that a single weakness at the top could bring everything down. A fortress's roof was its shield against the heavens, yet its design could invite a slow, internal death. The immense weight of a stone slab roof created a constant, crushing load on the walls below, but the true danger was far more insidious. Inadequate drainage meant that rainwater, instead of being channeled away, would pool and seep through the smallest cracks in the roofing. This relentless moisture would then be trapped within the dark, enclosed space of the roof structure, saturating the massive wooden beams that held everything up. In this damp, stagnant environment, timber rot flourished. Fungi would silently consume the heart of the wood, turning beams that looked solid into brittle, hollow shells that could no longer bear their burden. The Great Hall at Castle Stalker provides a haunting example of this decay. Its decline did not begin with a siege or a storm, but with years of minor, unaddressed roof leaks. Each drip of water that seeped past the slates was a tiny assault on the structural timbers, a persistent dampness that invited rot to set in and slowly devour the building's skeletal framework from the inside out. This internal erosion did not stop at the wood. Water that penetrated the roof would often run down the inside face of the outer walls, a hidden waterfall that the defenders could not see. Over time, this constant dampness washed the mortar from between the stones and encouraged mold growth that further degraded the masonry. The wall, designed to withstand a battering ram, was being dissolved by the very element it was meant to keep out. This underscores a profound truth that proper roofing is about more than just shelter. It is a critical system for managing the entire building's health. And just as trapped moisture could rot a roof from within, the lack of fresh air in other confined spaces created a different kind of structural threat. The air inside a fortress could turn to poison for its own bones. Within those thick, windowless walls, a silent killer was at work: condensation. Without adequate ventilation, the humid breath of hundreds of inhabitants, the steam from kitchens, and the dampness from laundries had nowhere to escape. This moisture saturated the still air, clinging to cold stone surfaces and seeping into every hidden cavity. the result was a perpetually damp environment where decay flourished unseen. The most vulnerable victims were the fortress's own internal supports. Iron bars and cramps, used to reinforce arches and bind stones together, would slowly rust and expand. This rust-jacking process exerted immense pressure from within the masonry, cracking apart stones that had stood for centuries. Meanwhile, the constant humidity attacked wooden floor joists, roof supports, and the frames of interior buildings. This rot did not announce itself with a dramatic crack. It was a slow, patient consumption that left the wood brittle and hollow. A stark example of this hidden decay occurred at Raglan Castle. One of its great towers, which had withstood sieges and cannon fire, experienced a sudden, catastrophic collapse. The investigation pointed not to an enemy, but to generations of trapped moisture that had rotted the crucial timber supports hidden within the walls. The tower did not fall in battle, it crumbled from within, defeated by the very air its defenders breathed. This flaw reveals a profound lesson in structural longevity, that a fortress must be designed to breathe. Simple ventilation shafts strategically placed to create a cross-draft could have carried this damaging humidity away, preserving the iron and wood that gave the stone its true strength. Yet, even the most clever defenses could be turned against the fortress in the most unexpected ways. Even the most ingenious defensive features could backfire with catastrophic force. Machicolations, those stone galleries projecting from the tops of walls, allowed defenders to drop rocks and boiling liquids directly onto attackers below. They were the ultimate expression of defensive control, yet their construction introduced a dangerous, overhanging weight that the wall itself had to counterbalance. This forward thrust created a powerful lever effect, pushing downward and outward on the masonry. If the supporting corbels, the stone brackets holding it all up, were not massive enough or perfectly set, the entire assembly could fracture and tear away from the wall face. The same peril applied to wooden hoardings, temporary covered galleries built out over the battlements during a siege. While they offered excellent protection and firing positions, their collective weight was tremendous. When saturated by rain, the wood became even heavier, placing an unexpected strain on the wallwalk and its supports. History records a dramatic failure of this kind during a siege of Dover Castle. A section of its defensive hoarding, overloaded with defenders and perhaps weakened by fire or rot, gave way. It did not simply fall, it ripped away from the wall, taking chunks of the parapet with it and creating a sudden, gaping hole in the castle's defenses where one did not exist moments before. This incident drives home a brutal engineering truth that every tactical advantage must be weighed against its structural cost. An addition that makes a wall more defensible can also make it more fragile if the wall itself cannot bear the burden. This delicate balance between offense and structural integrity extended even to the very staircases defenders used every single day. A fortress' own staircases could become its death trap. Those iconic spiral staircases, twisting upward through towers and keeps, were a clever piece of defensive design. Built to ascend in a clockwise direction, they gave a right-handed defender on the higher steps the room to swing his sword, while an attacker climbing up was hindered by the central column. But this tactical advantage came at a terrible strategic cost. The stairwells were often impossibly narrow, creating a single, constricted channel for movement. In the chaos of an assault, this was a recipe for paralysis. A single fallen soldier, a piece of rubble from a damaged wall, or even a dropped weapon could completely block the passage, cutting off an entire section of the defense from reinforcement or escape. The defenders could be trapped in their own towers, rendered useless while the battle was lost below them. The structural weakness was even more alarming. The entire staircase typically spiraled around a single central stone pillar, the newel post. This one column bore the weight of the entire stone staircase above it. It was a single point of catastrophic failure. If that central post was shattered by the impact of a siege engine, or if sappers managed to weaken its base, the entire staircase could collapse in a cascade of stone, severing vertical access completely. The historical record of Norwich Castle's Great Tower reveals this exact tragedy. During a period of intense conflict, the collapse of its primary spiral staircases left defenders stranded, unable to coordinate or retreat, dramatically accelerating the fortress's fall. This fatal flaw teaches a principle that modern architects apply to skyscrapers and fire escapes: the absolute necessity of redundant egress routes. A single path, no matter how cleverly designed, is never enough. And just as a fortress could be crippled by a lack of escape routes, its survival could be threatened by a failure at its most vital source of life, its water supply. A fortress could starve its defenders with poisoned water. While castle builders rightly placed their well inside the protective walls, its specific location was a matter of life and death. All too often, the vital water source was sunk perilously close to the garderobes, the castle latrines, and the midden heaps where garbage was discarded. During a rainstorm, runoff from these waste areas would seep deep into the ground, carrying filth and disease directly toward the well's water table. This invisible contamination transformed the castle's lifeblood into a slow-acting poison, leading to outbreaks of dysentery and typhoid that could decimate a garrison faster than any enemy army. A healthy, well-fed army was useless if it was too sick to stand on the walls. The siege of Château-de-Chinon provides a stark example of this peril. The defending forces, relying on their internal water supply, found themselves falling ill in droves. It was only through a combination of luck and perhaps a deeper, uncontaminated secondary spring that they avoided a complete collapse from within, a surrender forced not by broken walls but by a contaminated well. Beyond pollution, the well itself could fail. A well that ran dry during a long siege, or one whose opening was vulnerable to an attacker dumping animal carcasses or other poisons into it, rendered the entire fortress indefensible. A castle could stockpile food for years, but without fresh water, surrender was only a matter of days. This principle is so fundamental that it echoes in modern emergency planning, where securing a clean water supply is the very first step in any survival strategy. The life-giving well, when poorly placed, became an instrument of self-destruction. Yet another elemental force was waiting to exploit every hidden weakness in the stone, a force that could turn the strongest fortress into an inferno. Fire was a predator that could hunt a fortress from within. While thick stone walls deflected arrows and withstood boulders, they often encased a highly combustible core of wooden floors, roof frames, and internal buildings. A single stray arrow tipped with burning pitch, a cooking fire knocked over in the kitchens, or an enemy fire arrow lodged in a timber hoarding could ignite a catastrophe. The Castle of Stirling learned this lesson in a blaze of horror in 1296. A fire, once started, found an endless feast of dry, aged timber. It raced across wooden floorboards, climbed up interior walls, and roared through the skeleton of the roof. Thick, choking smoke filled stairwells and chambers long before the flames arrived, suffocating defenders and trapping them in a deadly maze. The stone shell remained, but everything inside was reduced to ash, rendering the fortress completely indefensible. The solution was a shift in material philosophy. Progressive builders began to use stone vaulting for crucial ceilings, especially over the Great Hall and Gatehouse, and coated internal woodwork with thick layers of plaster or daub. This was not just about comfort or aesthetics, it was a vital layer of passive defense, creating fire breaks that could contain a blaze and prevent the entire structure from becoming a self-made funeral pyre. Yet the very act of trying to improve a fortress over time could introduce a whole new category of danger, a slow accumulation of structural contradictions. Each generation of lords sought to leave their mark, adding a new tower, extending a wall, or updating the living quarters. These constant, piecemeal modifications created a patchwork of architectural styles and structural systems that often worked against one another. A new, heavier tower built onto an older section of wall could overstress foundations that were never designed for the load. Blocking up an old doorway to improve security might unintentionally divert water runoff into a vulnerable section of the foundation. Each alteration was a decision made with the best intentions, yet without a master plan. These changes layered hidden tensions into the fabric of the fortress, setting the stage for a slow, creeping collapse born from good intentions gone awry. A fortress was not a frozen monument, but a living entity constantly reshaped by the ambitions of its owners. Each generation sought to leave its mark, adding a new tower for a better view, extending a curtain wall to enclose more land, or building a more comfortable great hall against the old keep. These modifications were made with the best intentions, a desire to improve and modernize, yet without a master plan or any understanding of structural engineering. These piecemeal additions layered hidden contradictions into the very stone. A new, heavier tower built onto an older section of wall could transfer loads that the original foundation was never designed to bear. The ground, already stressed, would settle unevenly under this new weight, creating fresh cracks that snaked through both the new and old masonry. Blocking up an old gateway to improve security might seem like a smart move, but it could unintentionally divert rainwater runoff into a vulnerable section of the foundation, creating the chronic waterlogging we know is so destructive. The ad hoc nature of these projects meant that the fortress slowly evolved from a unified defensive machine into a patchwork of conflicting architectural eras, each one pulling against the others. We can see the legacy of this cumulative damage at Caernarfon Castle. Its majestic walls are a tapestry of construction periods, and over the centuries, sections that were added later, without a full integration into the original load-bearing scheme, experienced collapses and failures that the core structure withstood. The original medieval engineers built with a certain logic, a balance of weights and forces. Later builders, while skilled, disrupted that delicate equilibrium. The fortress became a victim of its own evolution, weakened not by a single enemy but by the well-meaning upgrades of its protectors. This reveals a profound principle that resonates in modern engineering and software design, that continuous, uncoordinated modification inevitably introduces complexity and fragility. A structure's integrity is holistic, and when you alter one part, you change the behavior of the whole. And just as these internal changes created blind spots in the structure, a failure to see the approaching enemy could create a fatal blind spot in the fortress's defense. A fortress could be rendered blind by the very landscape that made it strong. Perched high on a hill for a commanding view, it might still be betrayed by a dense forest creeping up its slopes or an unseen ravine cutting through the approach. These natural features, left unmanaged, created pockets of shadow where an entire army could gather, unseen by the watchmen on the towers. The defenders would only realize their peril when the first grappling hooks landed on the walls, the attackers having closed the final distance without a single alarm being raised. The infamous capture of Edinburgh Castle in 1314 serves as the ultimate lesson in this failure of visibility. Scottish forces led by Thomas Randolph knew the ground intimately. Under the cover of darkness, a small assault party scaled the treacherous northern cliff face, a route the English defenders considered impossible and therefore left unguarded. The castle's own formidable position, its high rock, created a fatal sense of security and a blind spot that was ruthlessly exploited. The fortress fell not because its walls were weak, but because its eyes were closed. Comprehensive situational awareness was not just a military tactic, it was an architectural mandate. A castle's design had to include the deliberate management of its surroundings, clearing forests for a clear field of view and ensuring that every potential approach route was covered by overlapping lines of sight from multiple towers. Without this total environmental control, the strongest fortress became a giant staring out at the horizon, completely missing the enemy at its feet. This brings us to the final and perhaps most human of all the hidden flaws, one that resides not in stone or soil, but in the hands of those entrusted with its care. The final and perhaps most tragic flaw was not one of design, but of simple neglect. Even the most brilliantly engineered fortress was a living system that demanded constant care, and when that care lapsed, the slow creep of decay was inevitable. Minor cracks in the masonry, if left unattended for just a few seasons, would be pried open by the relentless freeze-thaw cycle, transforming from hairline fractures into gaping wounds. Mortar joints worn down by wind and rain would crumble away and were seldom repointed, leaving the stones to shift and grind against each other without any binding agent. Wooden beams in roofs and hoardings, left untreated and exposed to dampness, would slowly surrender to rot and insects, their strength silently ebbing away until they could no longer bear their own weight. This was not a dramatic failure, but a slow surrender to time. We can see this story written in the crumbling stones of Harlech Castle. After the medieval period passed and its strategic importance faded, the cycle of maintenance was broken. The money and will to make small, continuous repairs evaporated. What armies could not conquer, simple neglect achieved. Roofs collapsed, walls began to lean, and the mighty fortress gradually became the magnificent ruin we see today, a monument not just to medieval power, but to the absolute necessity of upkeep. Regular maintenance is the unsung hero of structural longevity, a truth that holds for every engineered system, from a stone castle to a modern suspension bridge. A small, timely repair can prevent a catastrophic failure, proving that vigilance is the ultimate defense against time itself. These 20 hidden flaws reveal a profound truth about medieval engineering. The builders of these fortresses were not incompetent. They were pioneers operating at the very limits of their materials and knowledge. They created monumental achievements that still awe us today. Yet their failures teach us just as much as their successes. Each collapse, each breached wall, was a brutal lesson in physics, geology, and human nature, lessons that would slowly accumulate to shape the future of architecture and engineering for centuries to come. Medieval engineers were masters of practical application, working at the very frontier of their era's knowledge. Their understanding of forces like compression and tension was born from direct observation and hard-won experience, not from mathematical formulas or laboratory tests. They knew a thick, tapered wall felt stable, and that a round tower deflected shots better than a square one, but the deep physics of why these things worked remained a mystery. This empirical approach, built on generations of trial and error, was both their greatest strength and their most profound limitation. Without the tools to calculate stress distribution or to test the tensile strength of their mortar, they were essentially building on a foundation of accumulated tradition rather than proven science. A design flaw might lie dormant for decades, its weakness hidden until an unusually heavy snowfall, a sustained siege, or simply the slow, relentless accumulation of years finally revealed the miscalculation. We see this pattern repeated across the 20 flaws, from foundations that settled unexpectedly to towers that amplified seismic shocks. Each collapse was a brutal but invaluable data point in the long experiment of structural engineering. It is this very context that makes their achievements so remarkable. They built monuments that have endured for nearly a millennium using rule of thumb, keen intuition, and exquisite craftsmanship. Their failures were not born of incompetence, but of a knowledge frontier that had not yet been mapped. Every cracked arch and subsiding wall taught a lesson that would be passed down, refined, and eventually codified into the engineering principles we rely on today. The legacy of these medieval builders is therefore twofold. We inherit the breathtaking beauty of the fortresses that still stand, and we owe a debt to the ones that fell, for their ruins taught us how to build a safer, more resilient world. The fall of a great fortress was never a simple story. It was a slow unraveling, a chain reaction where one hidden flaw would expose and exacerbate another. A sinking foundation would stress the walls, causing cracks that let in water, which then froze and expanded, further widening the cracks and weakening the mortar. A poorly placed gatehouse straining under its own weight would become the focal point for an enemy's cannon, and the internal bottlenecks in the staircases would prevent defenders from mounting a counterattack. These were not isolated failures, but interconnected breakdowns of a complex system. The true lesson of these ruins is not that medieval engineers were unskilled, but that they were navigating a web of physical challenges without a complete map. Their legacy is a masterclass in the importance of holistic planning, where every element from the deepest soil to the highest parapet must work in concert. These stone skeletons remind us that resilience is not about being unbreakable, but about understanding and managing weakness, constant vigilance in design, construction, and, most importantly, upkeep is the only true defense against the relentless pressures of time and nature. We have now journeyed through the 20 hidden engineering flaws that brought down these mighty structures. We would love to hear which of these failures you find most compelling. Was it the silent betrayal of a weak foundation, the slow poison of a contaminated well, or the fatal beauty of an overloaded decorative feature? Share your thoughts in the comments below, and thank you for exploring this architectural mystery with us.